Hi again. In this video, I'm going to show you how to do super resolution deep learning model training. Basically this can be useful for training a model to improve the contrast in an image recorded using poor resolution compared to a high resolution scan, which is acquired as once, and then you can use that model on all subsequent scans at poor resolution. So it's a method that uses a deep learning tools using almost like a denoising model. And in this training, you will be able to follow the exact steps using this data that I've loaded in a session. And I've loaded it in your training data called KitKat aligned in a session file. So the session file can be opened. You could also find the same data and try to do it from scratch using on our website. You go to the objects.com and under resources, sample datasets, there are these datasets, and you will find KitKat chocolate bar and a high resolution sample of KitKat chocolate bar. Those two are not perfectly aligned, they are close, but it might be something to try yourself to improve the alignment. I will just show briefly how it's done. And actually, I will delete a lot of these objects here. I will highlight everything at the top and delete those. So we don't need all of that right now. I just left it there so that you can have a look at it if you need. Basically, we have the poor resolution scan or the full scan, which is a chocolate bar, which is looking like this. And we just need to contrast it in the correct way. So there's the chocolate bar. We can change its color a little bit. I don't know if that's necessarily better. And that preset has a focus enabled, which is not good. Okay, so that's not too bad. Sort of looking like chocolate. I guess you could improve it a little bit, but that's not the point of this video here. Now we're going to be looking at the high resolution scan. And when you have two images on image channels, the one on top gets preference. So if you want to see it, basically you need to reduce the opacity. It has already been reduced here. So you can see like that. And if you see there, it's a cylindrical volume with 0 pixels, black pixels on the outside. So what we need to do is we can turn the whole data by 90 degrees so that we just look at the chocolate in the correct orientation. Otherwise, I feel like I have to turn my head all the time. Basically, we need to align this data. You take the one on top and make it slightly reduced opacity, and then you use the translate rotate tools in each axis to just get it just perfect. And you can do that movement, the translation with the arrow keys on your keyboard until it's just right. You can also rotate it slightly if you look at the left and right, and you can do that in different axes. So you can do that here. In this case, it's already been aligned, so you don't need to do that in this case. But in this case, we can also, let's just get out of this. I don't know what's going on with my rendering. I think it's something with my graphics card, but the point is it's been already aligned. So you can play around with the alignment if you want, but it's ready to go. Now, the important thing for a super resolution model, we're going to be using a UNet model for super resolution training. The same UNet model as before, using regression. Basically, what we do is we tell the model that this is the input data, and this is what we want as output, this kind of quality. So we can just contrast it a little bit better for you so that you see that it is actually better. So there's a lot more detail in that scan. And if you look at the original data side by side, you look at that, there's a lot of different, more features visible and sharper edges. So this is what we're trying to achieve, to have this data looking something like this. So in order to do that, you need the two image data sets to be the same size and the same geometry. What that means is they need to be cropped with the same clipping box or same box shape. So we're going to take an interesting thing in Dragonfly is if you take if you click on one of these image channels and then you select the box shape on the bottom of the main panel there, it would fit a box around the maximum image pixels of that particular thing. If you were to make a box around, if you click on the full scan and put a box around it, you see the box edges up there. And the way that this works is then it also translates the pixel size when you extract structured grid, which I will do in the next step. So we're going to use the box from the zoom scan, and we're going to use that. First of all, we're going to crop a little bit here because we don't want the 0 pixels part of the training. And we just want to make it limit to the actual data, not pixels outside of the data. And we don't want edge pixels on the other axis either. So in this axis, we can just crop it a little bit. And we see that this is now all within the correct zoomed scan. So what we do now with this box, we right click and we say extract structured grid. And we're going to do that from the zoomed scan. So this is now the zoom, let's just call it a new image zoom. And if we do the same thing with not the zoom scan, so right click, extract structured grid, and you take this original Tomo Recon, which is the original scan, we can call it original. And because we have the same box, which is associated with a zoom scan, these two will now have the same pixel size. So how do you check the pixel size? You see the original scan had, if you look in the basic properties there, has 679 pixels over 16 millimeters total distance, which translates to something like 23 microns. And if you look at this one, it's almost 1000 pixels over 4 millimeters, which means it's almost 4 microns. With a zoom scan, we now have 500, the zoom cropped region, we now have 580 pixels over 2.7 millimeters, which is about 4 microns. And now on the original, we also have 583 pixels over 2.75 millimeters. It means the pixel size is exactly the same and it's following the highest resolution. Let's look at that in more detail. Let's put these images off, put the original on and the zoom on. We can, in both cases, just contrast a little bit. You don't need to do all of this. I just want to demonstrate how things work here. So if you look at this with the nearest, so that you actually see the pixels directly. This is the original scan, which was actually automatically downsampled. And this was the zoom scan, which looks like this. So if you look very carefully in this one, and you toggle these on and off, you see that the pixel size, if you keep your eye on 1 pixel, is identical. So the pixel size is identical. They are cropped in the same place. So the number of pixels in X, Y, and Z are the same. So this can be used for an input-output for a training. So this is what we're going to do as well. And what we also need, because we use the deep learning tool, we need a mask and we need a monitoring frame. So you could go as before, go to segment, make a new thing called mask. And we're going to paint a couple of single slices in the original scan, but it's actually just a mask of the same pixel size and width. So you could just do that. But let's say just for this demo, let's say that's enough. And Let's click on original and we go to AI. Now we're going to go to the deep learning tool. And what we're going to do is we're going to say new. We're going to choose a unit, and we're going to not pick semantic segmentation or denoising. This is a super resolution. So you have limited options. We're going to use UNet, and we're going to choose regression. And we can choose 2D for faster training in this demo. In regular times, we can let's do 2.5D. That's more useful in most general cases. Let's give it a name. This is a demo super resolution. 14 March. So the model is being generated, which before, so that you have something to train. And now we can close this panel. Now you see it here in the list. It's not trained, so we can go to training. For this, we take the original scan as input, the cropped original, and as output, the zoom scan cropped. So those two must have the same pixel size and number. Then we can choose the mask, and we can choose some data augmentation. Let's just do the standard. Let's do a bit less than standard, so we don't take too long here. And we have also a visual feedback. Oh, I didn't do that. Let's make a bit of a visual feedback frame somewhere. Let's look at, we go to main panel, select a little rectangle like that. Oops, that's not the rectangle, that's the auto contrast. Let's take the rectangle again like that. Okay, now we can select visual feedback. And just if I can see the train button. Okay, so there's an error, which is interesting. Now it might be as the error said that the mask is not big enough, that I might need to paint more pixels. It might be that the mask was in the wrong axis, because we need to be in the image plane. Let's just right click and choose the image plane, and let's clear the mask and try to make a new mask. So we select this. Three, 4, 5, 6. There's another 7. Okay, so we've got 7 slices. That should be enough. Let's go again to deep learning tool. Here we are. Let's choose again the mask, and we've got the region there, and let's choose train. Yeah, so I think it might have been the image plane problem, but if you ever get that message, then you'd need to create a bigger mask, more training data to go in as ground truth, or make the patch size smaller. Patch size is 64 here. All of that can be changed, as you've seen in previous videos. So now the preview frame is not in the image plane, so you won't be able to see much in the preview. We can stop that and go back and close and we can change the preview frame to be one of these things. Let's choose a nice slice here. Let's choose a main panel. Let's choose this here as a new, whoops, I need to get back here. Yeah, that's it. Region 120 and train. Now we will see the preview frame. So similar to the noise to void, you can change this to show the actual current, 100% the current inference versus the original data. And we can see how that improves over time. And you can then apply this model to the original data in the same way as with a denoiser model, or you can use the same approach, not only to do super resolution, but also super contrast, which is the same thing, just at the same, acquiring scans at the same pixel size, but same voxel size, but with, let's say, for example, a 3-hour scan versus a 10-minute scan, and enhance the contrast of a 10-minute scan with information from the 3-hour scan. So many things are possible. The aim here is to show you where the tools are and how they work and what is needed. Just while it's training, to repeat, what you need is you need to align the data sets together. You need to crop them using the same shape box, using an extract structured grid method, so that both are extracted using the same pixel size, so that you have the higher resolution pixel size for both. And those high resolution pixel size cropped regions are then the input and the output for training the model. And you can add some slices to a mask to tell it which to use as input. And that's it. Use a UNet 2.5D as always, and many different different options are possible. So it would be great to see what you achieve with these tools. A lot of things are possible. So I think I'm going to stop it there. You can see that it's sort of plateauing out, and I'm not going to try to create the best super resolution model in the world today. So once you close that, you save it and close, and now we can apply this to the original data. So we can put all of this off. We have the original data here, and on this particular slice, we can just go to main panel, go to image process, no, filter with AI, sorry. Here we choose the demo super resolution 14 March. I believe it's this one. And we can do preview for this frame. And that's the result. Not too bad if you look at that. So it does do an improvement, even in such a short demo. So that's it. That's all I wanted to show you here. That's great. Thank you for listening.